Alrighties, hello everyone and welcome to your pre-lesson video today on similarity. So let's get right into it because we have a bit to cover. So first thing we're going to go over today is properties of similar polygons. So essentially, remember, similar polygons, they have the same shape, and if two polygons are similar, then their corresponding angles are congruent and the corresponding sides are in proportion, which means that their ratios are going to be the same. And we're actually going to see in a second how we're going to find a scale factor. And I'll explain what the scale factor is, all right? So let's look at this example. So trapezoid ABCD is similar to EFGH. Now see how I didn't use the word congruent, because congruent means identical, right? But they're not identical. They are similar because they have the same shape, but they are different sizes, all right? So let's look. We know that ABCD is similar to EFGH because angle A is congruent to angle E, angle B is congruent to angle F, angle C is congruent to angle G, and angle D is congruent to angle H. All right. And now from here, so those are the angles. Now we're going to look at their corresponding sides. All right. So we know that AB would be let me rephrase that. So AB over EF would equal to BC over FG, and CD over GH would be equal to DA over HE. So they're all in proportion, meaning they have the same ratio, right? And you're probably going to ask me now, what do you mean by proportion, right? So if you remember earlier, when we first started, we did on proportions. That's what I mean by proportionate. They would have the same ratio. They are the same proportion. And now in geometry, we use a specific term, which is what we call a scale factor, right? So essentially, the scale factor is the ratio of the lengths of two corresponding sides. And how we would find that is we would take each corresponding side and put them as a fraction. So let's look. So 12 and 8 are corresponding sides. So we're going to put it as 12 over 8 equals to 3 over 2. So this is the scale factor for that side, right? Now we're going to do it for all of the sides to make sure that they have the same ratio, because if they have the same ratio, then they are similar. But if they don't have the same ratio, they don't have the same scale factor, that means they are not similar. All right, so let's look. 6 over 4 is again 3 over 2. 15 over 10, 3 over 2. 9 over 6, 3 over 2. All right, so because all of their scale factors are the same, that's why we know that this shape is similar. All right. Now, the next thing that we have is the angle-angle similarity postulate, and this states that if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar via the angle-angle similarity postulate. And there's some criteria to this, right? One is that the corresponding angles are equal, are congruent. Two, the ratios of the corresponding sides are equal, right? They have to be similar shapes in order for this to be, similar. All right, so let's look at this first example. So this and this are parallel of each other. So their ratios are probably going to be equal. There we go. Same with this, parallel, so their ratios or their sides are going to be equal. And then their angles are going to be equal because parallel sides, remember, are Z's, F's, and C's. Because of those, we would have congruent angles. All right, so that's why this is, yes, it's similar by angle-angle similarity postulate. Same thing with this. This corresponds to this corresponds to this, and this corresponds to this. And we know that their angles are going to be the same because it's an equilateral triangle. These two are, right? So that means their angles are all going to be 60. So yes, this is also going to be similar by AA. Now this, as you can see, their angles are different, and not only that, their the ratios of their corresponding sides are not going to be equal, which is why this is not similar, nor is it congruent either. All right. Now, you have any questions about this so far, bring it to your deep dive lesson. All right. Now into the nitty-gritty stuff, transformations. So transformation is essentially like how we are moving the shape. We're either making it congruent or similar depending on what kind of transformation it is, right? So with translations, reflections, and rotations, our shapes would be congruent, right? We don't change its size. But with dilation, it's not congruent, but it is similar because of we're just either making it bigger or smaller by a scale factor. And we'll actually see this in a second. All right, so let's look. Let's look at translations first. So if you remember translations, we did this a bit with our functions. Like we're moving it either left, right, or up or down, or we're, making it wider or narrower. Now we're doing it with shapes, right? So just recap. So a translation, is a transformation that moves every point in a finger the same distance in the same direction. So let's take an example. All right, let's look at this transformation, right? So this transformation moves the parallelogram. So this is the original, right? It moves it 5 units to the right and 3 units up, right? And now how we would write it is a little bit different from your functions. Now how you would write the transformation for this, the translation is x, y is your original. Now when we translate it, we'll write it as x plus 5, y plus 3. So we'll take the signs as it is, right? This means we're moving 5 units to the right, 3 units to the right. And this is for coordinate geometry, all right? So for translations in geometry, this is how we would write the translation formula. Now let's look at this next example. All right, so by the way, if you ever see like a small tick over there, this means it's the image. All right, so that means this is the original and this is the image. Based on this, we know that the shape moved 4 units to the left. 4 units to the left and 5 units up, which is why we will write this translation as x minus 4, comma, y plus 5. All right, now if you have any questions about translations, bring it to your deep dive lesson. The next thing that we have is reflection. All right, so reflection honestly can be across an axis or even just a straight line. I will actually see this in a second. So essentially, a reflection is a point, line, or shape reflected across a line or axis, as it appears if the axis is a mirror with the reflection on the opposite side. So let's look. There are a few cases. All right, so one is like the reflection across the x-axis has the same x coordinates but negative y coordinates. So after the reflection, look, x still the same, but the y coordinates are negative of it. Okay, so let's look. This is the original, the pre-image, original shape. Let's take point A. You have 1, 3. Now, if we were to reflect it across the x-axis, right, if you notice, the coordinates are a prime as 1, negative 3. Our x coordinate stays the same, but our y coordinates becomes the negative of it. That's why it's 1, negative 3. Same thing with b. It used to be 1, 1. b prime is 1, negative 1. Same thing with c. 3, 3, 3, negative 3. All right, and so this is how it would be across a reflection across the x-axis. Now for this one. So this is also a reflection across the x-axis. So we are just flipping all of these points, right? So their x coordinates are the same, but their y coordinates are flipped into the negative of it, which is why it looks a little bit messy here because this point is going to be here and all these other points are going to be here. So there's a small overlap and this is possible, and don't worry. This is the correct answer. There might be a small overlap. It might be a little bit confusing, but just make sure, as you are finding any of your transformations, honestly, write it down on the paper because it's a lot easier to see what your answers would be and how they would become. All right. Now, there's also a reflection across the y-axis, right? And when this happens, your x-coordinates becomes the negative, so it'll flip the signs, but your y-coordinates stay the same. So let's look. X becomes flipped, y stays the same. So original image, if you notice, all of their y coordinates are the same, but their x coordinates are flipped, the opposite signs. All right. Now, if you have a reflection across other horizontal or vertical lines that are not the x-axis or the y-axis, it's the same concept. So now, here are some steps. So consider the line an original object as one figure. Then we are going to translate the entire figure to the line of reflection that maps to either the x-axis for horizontal lines or y-axis for vertical lines. And then we're going to reflect the object over the axis. And then we're going to undo the translation from step 3. That is, if you translated the figure 4 units right, then we're going to translate the figure 4 units left. So let's look. Actually, our line of reflection is right over here. Okay, so let's take D, C as our original, and B, and then I'll find also, this will actually be our final answer. So what this step means is that let's take this. We're going to translate this to the line of reflection, right? So if we do this, it's 1, 2, 3. 3 units to the right. Okay? So that means what we need to do from this line of reflection is now we're going to do here. We're going to do 1, 2, 3. 3 units to the left. That's why point B is our reflection across, is our image. All right? Same thing here. 1 unit right, 1 unit left. That's why BA is the image. Okay? Now, the next thing that we have is the one that's a little bit more complicated, is a reflection across a straight line in y equals mx plus b form. So here are some steps. So one is we're going to create a line from each key point in the figure that meets the reflection line at a right angle. So if I were to draw a line, for example, it would be dot, 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 dot. Okay, so imagine that's a straight line, okay? And it meets here at like 90 degrees. Now we're going to extend this line so that the intersection point with the line of reflection is the midpoint. So we're going to just draw this until we hit a certain point, which I know in this case would be here. And so that means this right here would be the midpoint from here to here. That's why this is the image. All right. Now the other endpoint of this line is the corresponding point of reflection. That's why B prime here is the image. Now we're going to do the same thing for C. So we will draw the line, la 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 la. All right, this should be the midpoint. So now I'm going to extend the line until this actually does become the midpoint. So if I were to draw a line, boom, coordinate of C prime would be here. Same thing for A, midpoint, extend the line so that it does become the midpoint. So that means my coordinate of A prime should be here. All right, and that's how you would find a reflection across a straight line that's in y equals mx plus b. Now, same thing here, we'll do the same steps. We would extend the lines so that they, when it meets the midpoint, meets the line of reflection, that's the midpoint, and then we'll just extend some more until it is of equal distance, and so on. All right. Now, if you have any questions about reflections, bring it to your deep dive lesson. Alright, now rotation. So essentially a rotation is a point, line, or shape rotated about the origin, which is 0, 0, of the graph appears as if the origin is an anchor, right? So it's your center point, and the items rotate around it. So there are some formulas that would help you find the answer, which are these. So it depends on your coordinates. So and also we are normally basing it counterclockwise. All right, so they are going this direction. Okay, so now a rotation of 90 degrees, your original would then become negative y-x. So if let's say your coordinates, let's take this example. All right, so let's take that's A. Actually, that's not. Let's take C. Right, so your coordinates of C are negative 2, 4. Now, if I were to rotate it 90 degrees, then my coordinates for my image are going to be, so I'm going to take, for my x coordinate of my image is going to be negative y of my y coordinate of my original, right? So in this case, I'm going to take 4, and I'm going to make it negative I'm going to flip the side, so it's become -4. That means the x-coordinate of my image is going to be -4. And then the y-coordinate of my image is going to be the x-coordinate of my original. So in this case, it's just going to be 2. All right, which is why the coordinate of my, sorry, this is supposed, yeah, it's supposed to be -2. There we go. Okay, that's why the coordinate of my image here for point C is going to be -4, -2. All right, so this one just takes a little bit of practice to get into it. Now we have a rotation of 180 degrees. Our image is going to have the coordinates of -x, -y. So we're just essentially just flipping the signs for our x and y coordinates of our original, right? So if we take E, our original coordinates are -1, 2. Now to find the coordinates of our rotation of about 180 degrees, we're just going to flip the sides. So it's going to become 1, -2, as you can see. All right, and then for our last rotation of 270 degrees, so it's essentially like your 90, except your y-coordinate, it's going to be the y-coordinate, you're not flipping the sign, and your x-coordinate will be flipping the sign. So essentially what I'm trying to say is that the x-coordinate of your image is going to be the y-coordinate of your original, all right? And the y-coordinate of your image is going to be the negative x-coordinate of your original. So let's look at this example. Our original is 7, 0. All right. Now if we were to rotate it 270 degrees, that would mean our image would have coordinates of 0, -7, as you can see. All right, so I know rotations can be confusing, so if you have any questions, send me an email or bring it to your deep dive lesson. Okay. Now on to our last thing of the day, we have dilation. So like I mentioned very early on in this video, a dilation would make our shapes similar, not congruent, because their size changes, right? So now essentially, like I say, dilation is just changing the size of an object without changing its shape by a scale factor. So our image can be expanded, meaning it becomes bigger, or it can contract, which means it becomes smaller, right? And then here's a really good tip of knowing if it's going to be, become bigger or smaller. So if our scale factor is more than 1, so if it's like 2, 3, 10, our image is going to become bigger. And if our image is, less than 1, but so it's between 0 and 1, right? Like half, 1/3, 1/4. So essentially a fraction. All right, that means our image is going to shrink. It's going to become smaller. And if our image remains the same, which means like, its scale factor is 1, then it's just going to be the same size. Okay, now with a scale factor, it cannot be 0, and it cannot be a negative number, because a shape can't have, like, in terms of size, volume, area, it can't be negative, because then it doesn't exist, which is why scale factors has to be a positive number bigger than 0. All right. Now, to find the dimensions of the new shape, we are going to look at this example. So we have this formula. So we are going to take the dimension of the original shape. We're going to multiply by the scale factor to get the dimension of the new shape. So let's look at this example. Given that P is 1, 3, Q is 3, 1, and R is 1, 1, what are the coordinates of triangle PQR after it goes a dilation with scale factor 3? What about if it was a dilation with scale factor 1/3? So let's look at the first one with a scale factor of 3. So if I were to look, so you have original, let's see, we have original we have original P 1/3, and now as it goes through the dilation, it's going to be 1 times 3 and 3 times 3, right? So that means the coordinates for image P is going to be 3, 9. Now we're going to do the same thing for Q. So coordinates of original Q is 3, 1. We're now going to multiply everything by 3. So Q prime would have coordinates of 9, 3. And now for R. Again, we're going to multiply everything by 3. So there we go. Now we have the coordinates of the triangle after dilation with scale factor 3. Now we are also going to do the flip side. Alright. So for the flip side, we're still going to do the same setup. So P 1/3. We're going to multiply everything now by 1/3. Right, so that means that gives our P prime the coordinates of 1/3 and 1. Alright. Same thing for Q. We're going to multiply everything by 1/3. So that's going to give us, there we go, 1/3. And then finally, we're going to find the coordinates of R prime. So we're going to multiply everything by 1/3 for this dilation. To finally give us 1/3 and 1/3. Alright? And this is how you would find the coordinates after dilation. Alright? So, if you have any questions about any of the concepts that we went over today in Similarity, as usual, send me an email or message or bring it to your deep dive lesson. Alright? Thanks for tuning in and have a good rest of your day.